Okay, let's go ahead and get started. So today I want to continue with our development of Yang-Mills theory, that is to say non-abelian gauge theory. So let me just remind you of where we left off last time. Okay, is that working? Yeah. Let me just remind you of where we left off last time. Okay, this monitor. It's not working. Okay, let's hope that works. So last time we were, no, it stopped working again. Okay, I'm not quite sure. There. Okay, we'll just see. Anyone have any? I mean, it seems like it might be the connection. Maybe if I screw this thing up. Okay, sorry. Talk amongst yourselves. Okay, anyone have any bright ideas? Should I just wait? Now it's working? So if I don't do anything? Okay, let's just, okay. Well, we'll see. We'll see what happens. Okay. So non-abelian gauge theory is what you get if you start with a theory with some global symmetry. So let's say that we were considering, Jesus Christ. Okay, should we give up on this thing? I don't know. Is there something obvious wrong? It's missing a pin. I hope it's not an important pin. Okay, let's just, okay. This has not happened before, but okay. Seems okay? Okay, well, let's just see what happens. So, let's imagine that we started with a theory with some global symmetry. So let's say, for example, we had n fermions that we could arrange into a giant vector with components psi1 up to psi n, labeled by some index I. Here, each of these psi's, of course, is a 4-component Dirac spinor. And then the Lagrangian is something like psi bar I d slash minus m psi, where psi bar is the corresponding row vector made up of the conjugates of the Dirac spinors. And the idea is that we wish to promote the global symmetry, whereby we multiply psi by some unitary matrix V. So here V, as we discussed last time, is going to be some special unitary matrix, by which we mean that V dagger is the inverse of V, and the determinant of V is equal to 1. We wish to promote this to a local symmetry, where psi will transform by the multiplication of one of these SUN matrices. But now we can choose a different SUN matrix at each point in space-time. And the point is that to make an invariant action, so that the dynamics respects this symmetry, well, if you just take psi bar psi, then obviously that will be invariant under this local symmetry. But all of the kinetic terms involving psi times the derivative of psi will not be invariant. And so, as last time, when we were discussing abelian gauge theory, electromagnetism, we require some sort of operator that we referred to as the Wilson line operator, which will be some operator U that is a function of two endpoints, y and x, as well as some curve that connects these two endpoints, And that has the property that if you take u, y, x, and you multiply it by psi of x, you're going to get something that transforms as if it were sitting at point y instead of at point x. Okay? So it should have the property that u, y, x, psi of x, under a gauge transformation should look like it lives at point y instead of at point x. Okay. So what that means is that under a gauge transformation, under one of these local symmetries, u has to transform by conjugation, where we multiply by the operator v of y on the left and v of x dagger on the right. Yes, that was just a mistake that I swapped the order. Thank you. Sorry about that. Good. Okay. And so, for example, in the case of electromagnetism, this Wilson line operator is given by the integral of the one form a mu along this curve. So clearly, U is going to have to be an n by n matrix now, rather than just a number, because if, because here we're multiplying by V's on the left and the right. So U is some n by n matrix. And what I'd like to do is try and ask what the analog of the vector potential A mu is now that we're considering a SUN symmetry rather than the U1 symmetry of electromagnetism. So in order to do this, let's just stare at this formula for a second and notice that if we wanted to try and extract A from this formula for the unitary Wilson line operator, we would take y very close to x and start expanding in the difference between x minus y. And so let's see what happens if we do the same thing here when we try and study a non-abelian symmetry. So in particular, let's just consider U between 2 points, x mu and x mu plus epsilon mu, where epsilon is a very small vector. And let's imagine expanding this as 1 plus I epsilon mu a mu plus dot dot dot. So clearly in the case of a U1 gauge theory, electromagnetism, this is how you would get the electromagnetic potential from the Wilson line operator. So let's see what happens now if we do this for the non-abelian case. So here A mu is going to be an n by n matrix as well. So you can quickly see here why we often like to use an index-free notation, or rather, we don't like writing things out in terms of matrices and vectors, because A mu here now is an n by n matrix, and it's also a 4 vector, so it has 4n squared indices. So, I guess you can write a vector. It's very hard to write a 3-dimensional matrix on a piece of paper or even a blackboard. So we often like using sort of some compact notation where we suppress as many indices as possible. Okay, so now let's start with this expansion of U. Then the transformation rule says that under this gauge transformation, well, you get a V of y, which is x plus epsilon on the left, and a V of x dagger on the right. So just inserting our expansion of U at linear order in epsilon, this goes to V of x plus epsilon, 1 plus I epsilon mu a mu plus dot 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 times V dagger at x. And then the point is that we can take this expression here and we can expand it so that v at x plus epsilon is v of x plus epsilon mu d by dx mu v of x plus dot dot dot, so that now we're comparing a bunch of terms that are all evaluated at the same point rather than different points. And so if you insert that into this expression, what do you get? Well, you get 1 coming from a v of x times this 1 times v of x dagger, which is just 1. Then you get a term linear in epsilon coming from here, so that's plus v of x. Let's write that as I epsilon mu v of x a mu v of x dagger. Of course, A and V are all n by n matrices, so we need to be careful about the ordering here. And then we get another term linear in epsilon mu coming from this guy right here. So that's plus epsilon mu d by dx mu of V times V dagger, all evaluated at the point x. So that means that A mu under this gauge transformation is conjugated by the matrix V and picks up an additional term. So we have to factor out an I here. That's this I right here, just moved onto the other side of the equation, times d by dx mu of V times V dagger. So this is the expected rule for how the non-abelian version of the electromagnetic field will transform under one of these local symmetries. Now, just as an aside, there's a slightly different way that I could write this expression. So for example, I could use the fact that V times V dagger is equal to 1. And so I could take the derivative of both sides of this expression with respect to x mu, and you would see that d by dx mu of V times V dagger is equal to minus V times the derivative of V dagger. So that's a useful little trick. So we could also write this expression as V a mu V dagger plus I times V d by dx mu V dagger. Any questions on this so far? Good. And just as in the case of electromagnetism, we expect that we can use the new gauge field, A mu, to build an action that is invariant under these local symmetries. Okay. So let's see how that works. So remember that psi bar psi is always going to be invariant under one of these local symmetries. The problem really arises when you consider terms with derivatives. So let's just consider something like d mu of psi. So what happens to this guy under a gauge transformation? Well, it becomes d mu of v psi, which is v times d mu of psi plus a correction term that arises when the derivative hits the matrix V. And it's that second term that's problematic. So for example, if I were to multiply this on the left-hand side by psi bar gamma mu, then the psi bar would pick up a V dagger. So if you just had this term here, the V dagger V would cancel. But this term here is the one that's going to cause you problems. So let's compare that to the transformation rule for A mu that we wrote down up here. And you can see that this term right here is exactly what you need to cancel this term here. So in particular, if you think a mu psi, how does that guy transform under a gauge transformation? Well, that's v a mu v dagger times v psi, okay, minus I d mu v v dagger times v psi, otherwise known as v a mu psi minus I d by d x mu v times psi. So let's then consider the linear combination, which is the non-abelian analog of the covariant derivative, which is d by dx mu minus I times a mu. And I've chosen that factor of minus I so that under a gauge transformation, well, you get the first term, which is v times d mu psi, just because you have this term here and that term there. And then I've chosen that minus I so that this term here cancels with that term there. Okay, hopefully that minus I, yes. So hopefully that minus I was chosen correctly. And so what this means is that we now have a way of taking derivatives so that the derivative of psi transforms just like psi. In particular, it gets multiplied by a v on the left. So, for example, you could write down terms like psi bar d slash psi, and this is going to be invariant under one of your local gauge transformations. And the only price now is that our derivative operator has been modified by the addition of this a mu, which is a vector that also carries, which is also an n by n matrix. Are there any questions on this so far? Okay. So far, everything is mirroring fairly closely things that we said for abelian gauge theory, for electromagnetism. Things get a little bit more interesting if we follow the logic of electromagnetism, and we now regard this quantity a mu as a field, and then ask what sort of dynamics, and in particular, what sort of kinematic term we could write down for our field a mu. So what we need then is to ask what sort of quantity we could build out of a mu that is Lorentz invariant and can be added to the action. So in order to think about this, let's just remember that in the case of electromagnetism, we had F mu nu, which was d mu a nu minus d nu a mu, but could also be written as the commutator of two covariant derivatives. And so it's natural to ask whether a similar sort of quantity could be constructed for this new type of gauge field. So in particular, remember that because d mu psi just picks up a factor of v under a gauge transformation, this is true for any psi. That means that if you acted with two covariant derivatives, you could just evaluate this expression over here where psi is replaced by d nu psi, and you'll see that this guy picks up a factor of v under a gauge transformation. So you could then consider the commutator of two covariant derivatives, just as you did in the case of electromagnetism. And what is that? Well, that's the commutator of d mu minus I a mu with d nu minus I a nu. just as it was in the case of electromagnetism. Except when you imagine computing this in a non-abelian gauge theory, you need to remember that now A mu and A nu are n by n matrices, so don't necessarily commute with one another. So what do you get? Well, you get minus I times d mu A nu minus d nu A mu, along with a commutator term reflecting the fact that A does not necessarily commute with itself. A mu does not necessarily commute with A nu. So, in analogy with electromagnetism, we can define the field strength to be this quantity in the parentheses right here. So it has this additional commutator term. And the argument up here that d mu d nu psi transforms to v times d mu d nu psi tells us that under a gauge transformation, f is just going to transform as f mu nu goes to v f mu nu times v dagger. To check that, you can just take this transformation rule right here and consider this formula up here. So consider this transformation rule up here, and now take the commutator of d mu and d nu, and that's just equal to f. And so you can see that if f transforms to v f mu nu times v dagger, then indeed you'll just reproduce this transformation rule up here. So that was sort of a roundabout way, a very slick way of deriving the gauge transformation properties of f mu nu. Of course, if you wanted to, you could just go ahead and check this by plugging in the transformation rule for A into the definition of f. And you'll reproduce this transformation rule that I've written here. Now, there's one interesting thing that we should note, which is that in the case of electromagnetism, the field strength was independent of, is unchanged under a gauge transformation. In the case of Yang-Mills theory, we see that f mu nu isn't exactly unchanged under a gauge transformation, but rather that f mu nu transforms in a very simple way. Namely, it gets conjugated by the matrix V. And so sometimes we say that f mu nu transforms covariantly. That's one way that people refer to that transformation law. Also, sometimes people say that f mu nu transforms as an adjoint under the SUN gauge transformation. So that's using the language of group representation theory and the representation theory of Lie groups, which is something that we'll address, well, later on in this class and also probably later on this week as well. But the important point is that if we want to try and now construct a scalar quantity, which is invariant under the gauge transformations, you could imagine trying to construct something like f mu nu, just like you had in electromagnetism. But this guy will transform. It'll pick up under a gauge transformation with it'll be multiplied by a v on the left and a v dagger on the right. So if you want to write something that's unchanged under a gauge transformation, one of the things you could do is take a trace. Remember, F is an n by n matrix, so we can always take a trace. And this is going to be a scalar which is also invariant under a gauge transformation. And in fact, it's the only possible gauge invariant scalar constructed out of A that's quadratic in A that it's possible to write down. So it's the only possible choice for an action for a non-abelian gauge field. Question?
Can we find the unitary transformation that one is the commutator between A mu and A mu?
Sorry, can you make...
The definition of
Sorry, could you choose a gauge where the commutator of A mu and A nu vanishes? That's the question.
Yeah. This reminds me of the fact
Yeah.
that in the Riemann tensor.
Well, yeah, so this is... Yeah, okay, good. So this is... this should be reminiscent of the Riemann tensor. Okay. So remember, in general relativity, something I'm going to learn what CF stands for. I think it's Latin. In general relativity, one definition for the Riemann tensor is that it's the commutator of two covariant derivatives acting on a vector. And so you can see this is nearly identical to the definition of F. And in fact, if I hadn't suppressed, if I hadn't suppressed all of my indices and wrote out the matrix indices of F explicitly, then it would look even more similar. Okay. So it is very similar to the expression for the Riemann tensor in general relativity.
The Riemann tensor has two derivatives of the Christoffel symbols and then
Correct.
quadratic terms.
Yeah.
In a local inertial frame, then this quadratic term is fine.
Yeah, good. So those, okay, so those would be Gaussian normal coordinates. And so locally, I guess it's probably, yeah, I hadn't actually thought about that. I guess it's probably true that you could make a gauge transfer. I wonder if that, okay, I'll need to think about that. I think it might be true.
We can find the matrix be
Yeah, I mean, that's right. I think that's probably true. Right, yeah. Yeah. Is it obvious? Is it obvious to anyone? It's not. I think it's true. I mean, the idea, at a point, A mu, A nu, A1, A2, A3, A4 are just four n by n matrices. And so I think you can choose a gauge where they will be mutually commuting. Yeah. Yeah. But I mean, the important point is that just as the Christoffel symbol in general relativity is not a tensor, the gauge field in a Yang-Mills theory does not transform covariantly under a gauge transformation. It picks up these extra terms. Yeah, that's a good question, actually. Okay, so anyway, we found the unique gauge invariant scalar that's quadratic in A. So that means that the most general Lagrangian that you could write down that is a gauge invariant scalar, so that your theory is Lorentz invariant as well as gauge invariant, will involve a kinetic term for the gauge field, again with an arbitrary coefficient that I've called 1 over 4g squared, along with a coupling term between psi and our gauge field, where again d here is defined in terms of the covariant derivative d mu minus I a mu. And this, as I have written it, is Lagrangian for SUN Yang-Mills theory. And the statement that we have, so this is actually not the most general sort of SUN Yang-Mills theory that we could write down. You could actually, as we'll learn later on in this class, couple it to many sorts of different types of matter fields. And so this SUN Yang-Mills theory that I've written down here is SUN Yang-Mills theory with matter transforming in what is known as the fundamental, or n, of SUN. So that last phrase that I put in quotes is something that we'll explain by the end of class today, or early next class. Okay. Any questions before I continue? So, yes.
This mass term, is it the same for all n spinors?
Yes, the mass term has to be the same for all n spinors because our action has to be invariant under psi goes to v psi. And in particular, v could interchange, say, psi 1 and psi 2 or something like that. So if you think about it, hopefully you can see pretty quickly that if psi 1 and psi 2, say, had different mass terms, then you wouldn't have that global symmetry where you can rotate psi 1 into psi 2. Is that more or less clear?
Yeah, but if we have more than one type of fermion,
Oh yeah, if you have more than one type of fermion, then you could have different types of mass term. So we'll get to that. So in particular, this n here is labeling an irreducible representation of SUN, and so you'll see that you could actually have a bunch of different matter fields transforming in different irreducible representations of SUN, and there could be different mass terms or couplings associated with them. So we'll get there. Okay. So far, we've written everything sort of abstractly in terms of n by n matrices. But it's useful to write out explicitly the indices of these n by n matrices. And so what I'm going to do next for at least a few minutes is give you a sort of brief, slightly schematic introduction to the theory of Lie groups, which is the mathematics that really sort of underlies our description of this set of n by n matrices. So the idea is very simple. I mean, when you talk about Lie groups and representations of Lie groups and Lie algebras, sometimes the terminology can be a little strange sounding, but it's all actually really quite simple. The idea is the following. So let's just consider one of our special unitary matrices, SUN, and let's just imagine expanding it near the matrix 1. So we'll think of it as 1 plus I theta A Ta plus terms that are higher order in theta. And if you like, you could think of this as the first term in the expansion of V as e to the I Ta theta A, where the Ta are some n by n matrices that are Hermitian because V is unitary, and they're referred to as the generators of the Lie algebra SUN. And A here is an index that runs from 1 up to the dimension of SUN. So the group SUN is a group of n by n matrices. It has a dimension just like any other space, and it's a dimension that we'll compute in just a second. And as we introduced very briefly last time, because these TAs are supposed to form a complete basis, when you exponentiate them, you're supposed to get any SUN group element, they must obey some rule where the commutator of any two T's can be written as some sort of, as is linear in the T's themselves. Remember, I think we did this last time. This is basically the Campbell-Baker-Hausdorff lemma. If you take two V's and multiply them together, you have to get another V. And so if you write V as an exponential here, then the first term that you get is a commutator term. And so the commutator of any two T's has to be some linear combination of the T's. where these constants f, a, b, c are referred to as the structure constants of our group SUN. So if you want a simple example, you could think of SU2, where the T's are given by the Pauli matrices, and the structure constants are just the epsilon symbol, epsilon ijk. That's the commutator algebra of the Pauli matrices. And the fundamental property that is obeyed by these structure constants is known as the Jacobi identity. So that's the statement that the commutator of TA with TB and TC plus all of the various cyclic permutations has to vanish. So this is an elementary formula to prove if you just write it out using commutators. But I'm emphasizing it for reasons that will become clear in just a second. And if you stare at this formula for a second, you can see that this implies that the structure constants f, a, b, c have to satisfy some sort of quadratic equation. So for example, that first term, the commutator of TA with TB and TC, what is that? That's FADE, FBC, what is that? FBCD, and then plus the various other terms, so there's an FBDE, FCAD, and a final term, FCDE, FABD, all has to be equal to 0. So here all I've done is I've inserted this expression for the commutator into here, used the commutator twice, and taken as E my free index that labels, so the triple commutators here are going to be proportional to something times TE. And so this gives us some sort of quadratic equation for the structure constants. So if all that index manipulation wasn't quite clear, don't worry. I'm sure you'll have fun verifying it for yourselves at some point. It's all pretty straightforward. So yes?
Can we find general solution to this last equation?
Yes. Yes. I mean, yeah. So let me. Okay. That's where I'm sort of getting. Okay. So so far I've introduced the TAs as n by n matrices that come when you expand a unitary matrix near the identity, and I've just observed that they obey this Jacobi identity. But abstractly, what we do is we think of a Lie algebra as a vector space with basis elements TA which obey a commutation rule. The commutator of TA with TB is FABC TC. And those structure constants are constrained by the fact that they obey a Jacobi identity. So this is really a very nice way of thinking about gauge theories and thinking about theories with this local symmetry. Because, as we'll see, I mean, as you're probably familiar with from the representation theory of SU2, there are many sorts of different representations of SU2. And they're and you achieve these representations when you think of, say, the rotation generators as abstract group elements, and then you look for all of the matrices that obey that commutation rule, and that gives you all of the different representations of SU2. So for example, that's what gives you the fact that there are particles of spin 1/2 in quantum mechanics for any half-integer spin. And the point is that once you assume that this commutator satisfies the Jacobi identity, then that implies, really, that these TAs can be exponentiated to form a group, and a continuous group that's obtained by the exponentiation of these Lie algebra generators is referred to as a Lie group. So a Lie group is just a fancy name for a group where the group elements are labeled by continuous parameters rather than discrete parameters. And so it has some, it's a manifold in the mathematical sense, and it has the sort of continuity and topological properties that you expect of a manifold. But from a sort of physics point of view, you can just think of it as a group whose elements are labeled by some continuous variables rather than discrete variables. Okay, so let's just, to get our intuition, let's just think of a few examples of Lie groups. So the simplest example of a Lie group is U1. That's, if you think about U1 explicitly, that's just the group of 1-by-1 matrices, i.e. complex numbers. And there's a single generator. Okay, you think of an arbitrary complex number with determinant 1, so that the norm of that complex number is 1, as e to the I theta times t, where t is just a single element. Well, it's really just 1. It's just the single generator of U1. And this Lie group is, nearly trivial because the dimension is equal to 1, and all of the structure constants are just equal to 0 because the commutator of t with itself is equal to 0. And in fact, it turns out that Lie groups can be completely classified. And you've already seen a lot of the different types of Lie groups. So in fact, the classification of Lie groups, the fact that they can be classified at all is very interesting. It gives us a classification of the possible non-abelian gauge symmetries that could ever arise in physics. The classification is not too difficult, but it involves a lot of combinatorics, and it would take us pretty far aside from really where we're trying to go in this course. So I'm just going to quote the result for the classification of Lie groups for you, rather than trying to prove it for you. So the classification of Lie groups basically is as following. So any Lie group with an element T that commutes with all other generators is referred, that just has a U1 factor. And so you could just go ahead and throw out that generator and look at the ones that are left over. And so we refer to a semi-simple Lie group and that's just one with no U1 factors. So every Lie group is going to be a semi-simple Lie group along with a bunch of U1 factors. So for example, the group of unitary n by n matrices is not semi-simple, but the group of SUN matrices is semi-simple, and UN is SUN times U1. Why is that? Well, SUN is the set of unitary matrices with determinant equal to 1. But you can pull out an overall phase factor from a unitary matrix. And so any unitary matrix is an SUN matrix times a phase factor. And if you think about it for a second, in the group multiplication law of two unitary matrices, each of which is written as SUN times a phase, the phases just multiply in exactly the way that you expect phases to multiply, and the SUN matrices multiply in the way that SUN matrices multiply. You can commute all of the phases through. So if you're just thinking about Lie groups, you can just forget about that U1 factor or just treat it separately. So for example, SU2 times U1 is another name for U2. So that's a semi-simple Lie group. And a simple Lie group is one where it's impossible to partition all of the generators into two groups which don't commute with one another. So, for example, you could imagine that it's possible to partition the generators of some Lie group into two separate algebras, both of which don't talk to each other. So the simplest case would be, for example, if you had, say, two copies of SU2. So then that would be that's a semi-simple but not simple Lie group, just because you have two copies of those SU2 generators that don't talk to one another. Does anybody know another name for that group? Out of curiosity. It's SO4. Otherwise known as the rotation group in 4 Euclidean dimensions, otherwise known as up to a factor of I, the Lorentz group. Remember, we probably did this at the beginning of this course last semester at some point. The Lorentz group is just basically, you remember these J's and K's, right? The J's and K's, were the generator of boosts and the generator of rotations. And from those you constructed two commuting SU2s. I guess we called them N was J plus IK, and dagger was J minus IK. That's a slightly different example from here because those two SU2s were not generated by Hermitian generators, but at the level of the algebra, you had two commuting SU2 algebras. Good. And so the theorem is that every simple Lie group is either one of 5 exceptional groups, which we'll talk about in a second, or it falls into one of 3 families. So, for example, the first family is the group of SUN matrices. So this is the set of unitary matrices with unit determinant. And if you want to think a little bit sort of more abstractly about how you define unitary matrices, they're defined as the set of linear transformations that preserve an inner product. And it's the inner product, that we demanded was invariant. So for example, psi bar psi is an inner product between an n-component column vector and an n-component row vector. And when you multiply by a unitary matrix, it's left unchanged. Similarly, SON is the set of real n by n matrices with R transpose R is equal to 1. And again, the S means that the determinant is equal to 1. And this preserves the n-dimensional dot product. So if you have two vectors in n dimensions, their dot product is preserved under an SON rotation. And so that's also something that's probably familiar. So SO3 is the example everyone knows. And the final example, which is one that is maybe a little bit less familiar, although it probably shouldn't be, is the n-dimensional symplectic group. So this is also a set of n by n matrices, but they obey a slightly different sort of algebra, a slightly different identity. So here omega, so here the v's are 2n dimensional, so they have to be even dimensional. And omega is, if you think about it as a 2 by 2 matrix, each of whose blocks are n-dimensional matrices, is just the matrix 0, 1, minus 1, 0. So, and this preserves a different sort of inner product. So it preserves, for example, if you have 2n component vectors phi, it observes something like that. Okay. So does anybody know what the physics structure is that you've already seen that is preserved under symplectic transformations? Yeah, so let's put it this way. You know that the vector inner product is preserved under rotation. There's something that you guys have all seen that's preserved under the symplectic inner product. It's the Poisson bracket in the Hamiltonian formulation of mechanics. So phase space, P's and Q's naturally have a symplectic structure, not a vector structure. And so, so the symplectic transformations do also appear all over the place in physics for precisely that reason. So these are the three basic families of Lie groups. And the exceptional groups are sort of cool. We're not going to study them at all in this class. But they have names, and I'll tell you those names just so that you're not freaked out the next time you hear someone talk about them. So there are 5 of them, G2, F4, E6, E7, E8. Okay? And every once in a while people will come up with theories of physics based on some of these exceptional groups. Okay? And they're all very closely related to these other groups, the more familiar groups that you already know and love. In this class, however, we're going to focus entirely on SUN. So we're not going to bother with these other types of Lie groups. But I just thought it was important to mention this classification because in some sense this is a classification of the types of symmetries, continuous symmetries, that are allowed in physics. Any questions on this? No questions? Yes.
What is the classification of those three?
The Dynkin diagrams. Okay, now I'm going to be embarrassed. So the classification is based on the Dynkin diagrams. So SUN is that, where you have n dots that are all connected by lines. And I'm embarrassed that I don't actually remember what the Dynkin diagrams for the other ones are. The exceptional groups are something like that. And then there's the various, I don't remember what the Dynkin diagrams for the other groups are. I think you need double lines for some of them. I probably should remember what the Dynkin diagrams for all of these are, but I don't.
But which one of those should be A, B, C? Which one would be A, B, and C?
The SUNs are the A's. Right. So people sometimes talk about the ADE classification of Dynkin diagrams, and that's another name for the class. So this is not something we need to talk about in this class, but the classification of, so the way that this theorem is proved is it follows from the classification of some sort of combinatorial data associated with the group, and that turns into a classification of a certain set of diagrams known as Dynkin diagrams. It turns out that that classification of Dynkin diagrams is a classification problem that appears all over the place in mathematics. It appears in finite groups as well as in continuous groups. It appears in the classification of certain types of singularities that are allowed and stuff like that. But I don't want to get into it because I don't remember it terribly well. But everyone should learn it once, maybe even twice, but no more than twice. Good. Any other questions? It's all actually reasonably straightforward. I mean, there's this great book by George I on Lie algebras or Lie groups in particle physics, where he goes through this, and it's sort of fun, but it's nothing terribly fancy, just a lot of math. Good. Okay, so now what I want, yes, question.
And why are we going to focus only on SUN? Is there a particular reason?
Because SUN is the group that appears in the standard model of particle physics. SU3 times SU2 times U1. Now, there are other sort of variants of the standard model of particle physics which involve other sorts of groups. So, for example, it may be that the gauge groups of the standard model are unified into an SO10. I personally happen to like that model. I think it's the most economical, and there are other models where it's unified into exceptional groups and stuff like that. But for the standard model of particle physics, it happens that the only groups that arise are the special unitary groups. Good. Any other questions? I mean, the SO groups are very similar to the SU groups. Most of the things that we'll say can be general. I mean, all of those three classes of groups are very similar. So a lot of things, as far as what we're going to say in this class, everything is going to would generalize almost immediately to any of these other Lie groups. Indeed, a lot of what we're going to do is work in sort of an abstract index notation where you just do all the calculations, and at the end of the day, you plug in the structure constants. Okay, and the only difference between these groups is the structure constants. Good. So, for example, on a problem set, I'll probably have you work out the structure constants of SU3 or something like that. So the SU3 version of the Pauling matrices, which are known as the Gelman matrices, and their commutator algebra. Have you guys done this before? If you haven't seen this before, everyone should do this once and only once, maybe twice. Okay, good. So let's continue. Okay. So let's now understand some of the properties of these matrices TA and these structure constants FABC. So the first thing that we want to, so let's just focus on the case of SUN. So for SUN, our group is given by a bunch of matrices V that can be expanded in terms of these generators TA, where you have some constants theta that are the coefficients in this expansion. And the statement that the determinant of V is equal to 1 can be translated into a statement for the T's. And the easiest way to do that is just to remember that the determinant of a matrix is the exponential of the trace of the log of the matrix. Okay. That's a very nice formula if you haven't seen it before. And so if you plug that in, that's the exponential of the trace of theta A TA times I. And that has to be equal to 1 for all values of theta. So that implies that the TAs are traceless Hermitian matrices. So if you want to count the dimension of SUN, which I'll just call D, we just need to count the number of traceless Hermitian n by n matrices. So what is that? Well, a Hermitian n by n matrix, let's just think about a Hermitian n by n matrix here. Okay. A Hermitian n by n matrix has to have, well, it has to be equal to its adjoint. So that means that the diagonal entries must be real numbers. So you have the dimension is you're going to have an n in the dimension coming from counting those real numbers. And then all of the off-diagonal elements are complex. And because t is equal to its adjoint, you only have to specify the upper triangular part of the matrix in order to specify all of those complex entries. So a complex number has 2 degrees of freedom, and there are n times n minus 1 over 2 elements in that upper triangular part of the matrix. And then you have to impose the fact that the matrices are traceless. Okay? So the sum of the eigenvalues has to be equal to 1. So you subtract off 1 from that, because one of the eigenvalues is constrained by that. So that, if I have done everything correctly, should be n squared minus 1. As a check, when n is equal to 2, this gives you 3. Dimension of SU2 is 3. When n equals 3, the dimension is 8. Okay. One other observation that I'll make about SUN is the following. So we saw that the Hermitian matrices were traceless. So let's now consider the trace of the product of 2 of these matrices. Okay. So this is now a D by D matrix, little d by little d matrix. Okay. I've traced, so the n by n index has been traced out. It's not there anymore, but it's a d by d matrix. And if you think about it, this has to be a positive definite matrix. Because the TAs are Hermitian. In particular, if you use the fact that T dagger is equal to T, and you use the fact that the trace is cyclic, then this means that D is a positive definite matrix. So there is a basis where it is proportional to the identity. In particular, there's a basis where D is going to be diagonal, with positive real eigenvalues. And then you could just rescale all of the generators, rescale all of the T's to make D proportional to the identity matrix. So that means that in some basis, which is the basis that we'll be using from now on, this D is proportional to the identity. And I guess we could set that C equals to 1. I'm going to keep that C around because later on when I talk about the representations of the Lie algebra, that C is going to be, it's going to be necessary to keep that value of C. But you can then, if you think about it, use this basis to write the structure constants. So I claim that the structure constants can be written as the trace of the commutator of TA and TB with TC. Okay. So to see that, let's just use the expression for, so TA with TB is I times FABE times TE, but then we've gone to a basis where the trace of TE, TC is just delta EC. So that means that FABC is just proportional to this guy here. Or if you want to write this out a little bit more explicitly, I over C trace TA, TB, TC minus trace of TB, TA, TC. And you can now use the fact that the trace is cyclic to think about this as the sum over all orderings of the operators, TA, TB, and TC, times the sign of the ordering. So I guess you would call that the sign of the permutation sigma of T sigma A, T sigma B, T sigma C. So the point is that you can think of FABC as the sum over all different ways of taking the trace of TA, TB, TC, all different permutations, weighted by the sign of that permutation. And that makes it clear that in this basis, FABC is antisymmetric in its indices. Now, whenever anyone makes a statement to you about Lie groups and Lie algebras, the first thing that you should do is immediately think about the case of SU2. And indeed, for SU2, the structure constants are the epsilon symbol, epsilon ijk, which is antisymmetric in its indices. So indeed, you could check, for example, that the trace of two Pauli matrices, the trace of sigma I times sigma j, is proportional to delta ij. Yes?
Is that the determinant on a matrix with T's in the column?
If you have a 3 by 3 matrix, then this is the expression for the determinant. Almost, right? It's if you had a 3, let's see, what is it? If you had a 3 by 3 matrix, and the T's, yeah, something like that. It's not quite, but yeah, I mean the expression for determinant is a little different, but it's close to that one. You can think of it, it is a sum over permutations, though, in this way. Yeah, that's right, with all of the signs added on. I mean, if you have I think that is literally the determinant formula for a 3 by 3 matrix. Okay, any questions? Yes.
So this is a mathematical calculation, and it's a general confusion about the
Yes, there is a basis where F is antisymmetric. Yeah. Now, of course, there are other bases where it might not look antisymmetric. So, for example, if instead of sigma 1, sigma 2, sigma 3, you use sigma plus, sigma minus, and sigma 3, then it won't look antisymmetric. That structure constants would not be real and antisymmetric. Good. Okay, so what is the point of all of this? The point is that the gauge field A mu lives in the Lie algebra. So I told you that V was the unitary matrix describing the gauge transformation, and it's an n by n matrix. And A is also an n by n matrix, but it doesn't live in the same space as V. A lives in the Lie algebra, whereas V is an element of the Lie group. So for example, that means that you can expand A mu using the summation convention, where we sum over A, as A mu A TA, where now these A mu A's are just numbers, not n by n matrices. And these TAs are the generators of SUN. So, for example, an SU2 gauge theory is one where you have 3 gauge fields, 3 versions of the electromagnetic field, A mu 1, A mu 2, and A mu 3.
So is there an analog of that in GR?
Well, in GR, when you write a Christoffel symbol, you always write it in index notation. I mean, GR is slightly different because here we have 2 different varieties of index. You have the mu index, which is a space-time index, and you have the what I call the Lie algebra indices. In general relativity, the vector space that's transforming is the tangent space.
Yeah, yeah.
So the Lie algebra indices are space-time indices in the case of general relativity.
Okay, so
There are ways of phrasing general relativity so that it looks much more like a gauge theory. Okay. So there is, for example, what's called the Cartan formulation of general relativity, which is basically rephrasing general relativity in a way that looks much closer to the language of the gauge theory.
So if we were, example, if we were doing a infinitesimal diffeomorphism and this diffeomorphism has some generator,
That's right.
then
Yeah, you can think of infinitesimal diffeomorphisms as a gauge transformation, absolutely.
so these TAs that we have here can be the generators of the diffeomorphism.
Absolutely, yeah, absolutely. I mean, a generator of a diffeomorphism, otherwise known as a vector.
Yeah.
Okay. And so, for example, the covariant derivative d mu minus IA would be written as d mu minus I a mu TA, summed over that index A. And likewise, F mu nu involves derivatives of A, and so it's also an element of the Lie algebra. So we'll write it as F mu nu A, TA. And if you work it out, well, we already sort of saw this. So F mu nu is d mu A minus d nu A minus the commutator. And what is the commutator? It's a bunch of structure constants. So you'll get F A B C A mu B A mu C. And in writing this formula, I've been freely reordering the indices using the fact that the structure constants are antisymmetric. So it's frequently much more convenient to write everything out in this index notation than just thinking about abstract n by n matrices. Okay. Let me make just one or two more comments. So we saw that a finite gauge transformation was psi going to v psi, and if you expand, v is 1 plus I theta A TA plus dot dot dot, you can write the formula for an infinitesimal gauge transformation. Where the variation of your field psi is just I times theta A, now as a function of x, TA acting on psi. And likewise, the variation of our gauge field, so here, let me just remind you what that was. So under a gauge transformation, A mu went to V, A mu, V dagger, minus I times D mu, V, V dagger. So the variation under an infinitesimal gauge transformation, well, that second term, if you just plug in this guy up here, so V dagger is 1 minus I theta A TA plus dot dot dot, using the fact that the T's are Hermitian. So that second term is d mu theta A, writing it out in a particular basis. And this first term expanded out, well, it gives you A mu plus the next term is the commutator of A with theta A TA. So that's going to be plus the structure constants coming from the commutator, A mu B theta C. So if you compare this to what we had for electromagnetism, this is something that looks very much like the transformation rule for the electromagnetic field under a gauge transformation. But this second term is new. And just like this second term here in our formula for the field strength is new. Okay. So let me just end by making one or two more comments about Yang-Mills theory. So the first comment I'll make, and this is something that I think I'll have you prove on your next problem set, is that the equations of motion of Yang-Mills theory, so those follow from the Lagrangian. So 1 over 4g squared trace f mu nu minus the matter term involving the appropriate covariant derivatives. So in electromagnetism, so let's just ignore this matter term for a minute. So in electromagnetism, the equation of motion is Maxwell's equation. So that says that d mu f mu nu is equal to 0. When you have Yang-Mills theory, you actually get a correction to this equation, which takes the form f a b c a mu b f mu nu c. Here, I guess I need to lower an index to make everything work out. So if you have no matter, then that's equal to 0. And if you have matter, that's equal to some current, which now, has a free index, an additional gauge theory index A. And so in the present case, where you have this matter here, J nu A is psi bar gamma nu T A psi. So there's a lot of crazy indices floating around here. This non-abelian stuff is not going to be terribly familiar to you. You just really have got to start writing down these equations and working it all out, or else you'll never get used to it. So next class, I'll give you a giant problem set. We'll get lots of fun practice doing that. But let me end by making two just sort of interesting points about Yang-Mills theory that I think are worth keeping in mind. So the first point that I want to make is that the equation of motion of Yang-Mills theory is nonlinear in A. So even if J is equal to 0. So one of the most important properties of electromagnetism is that Maxwell's equations are linear. If A1 and A2 are two solutions of Maxwell's equations, so is A3. That's what leads to wave phenomena. That's what leads to constructive and destructive interference. That's what is the basis for every solution for solving Maxwell's equations. Yang-Mills theory is nonlinear. Okay. That means that it's a much more difficult, just solving the Yang-Mills equations for classical solutions is much more difficult than it is in electromagnetism. So general relativity is another example of a theory where the equations of motion are nonlinear, essentially for the same reasons that the equations of motion of Yang-Mills theory are nonlinear. And both of them are in general very difficult to solve, except in special situations where you have some symmetry. Physically, what does the nonlinearity of Yang-Mills theory mean? It means that gluons, which are the analog of photons for the Yang-Mills field, will bounce off of one another. They interact with one another. So a photon does not scatter off of another photon. But gluons can scatter off of one another. In particular, if you just wrote out explicitly this Yang-Mills Lagrangian, as we will do so, you'll see that there is a 4-point function, well, both a 3-point and a 4-point function for gluons. The final comment that I'll make is that Yang-Mills theories may appear to be complicated, and there's some sense in which they are complicated. But Yang-Mills theories are the only renormalizable theories containing vectors in 4 dimensions. I should say really non-trivial renormalizable theories. There are trivial theories that have no interactions. But if you want to construct a renormalizable theory that is a non-trivial theory in the infrared involving vectors, it's got to be a Yang-Mills theory, or else it's trivial. So to some extent, Yang-Mills theory is incredibly natural. We already started this course by discussing scalars and zero particles. And then we moved on to spinors, spin 1/2 particles. Now we're on to spin 1. And Yang-Mills theories are essentially the only renormalizable theories that we can write down. Good. Okay, so I'd like to stop here. Next class I'll move on to do a bit of representation theory. But maybe before I end, I should see if there are any questions. Okay, great. See you on Thursday.